We're very happy that GA Shan can visit today from Cornell to tell us about her work. She got her PhD from Columbia University, then went on to be junior faculty at Case Western, and also junior and full faculty at Penn State before moving to Cornell in 2018. She's an expert in, I think, things that are very interesting to us, 2D materials, including graphene, molybdisulfide, and other transition metal dichalcogenides, as well as the heterostructures. In particular, a very interesting thing recently is what we call Twistronics, where you take a couple of these layers, twist them, and lay them on top of each other, and you end up with getting a Moire pattern that gives you a much lower density electron gas to fool around with. And that's what I believe that she's going to tell us about today. So thanks very much for coming. Thanks.
Well, thank you, Bob, for the introduction and for the invitation. So before I start, I would like to thank my team who actually did the real work. So Professor Kim Van Mack co-supervised the group with me. And the bulk of the material I'm going to present today are the work of Yang Shi, Yang Hao Tang, Ting Xin, graduate student Li Zhong, and a younger one, Raymond, and another postdoc, Shen Wei. We've been also very fortunate to work with some of the theorists, some of them you know very well. Alan McDonald, Liang Fu, your local guy, and also Vi Elsa, my local colleague at Cornell. And the work wouldn't be possible without the high quality bulk crystals from Columbia team led by Jim Hong. And as everybody else, you know, we got our boronitride crystals from Japan. So let's first just to consider an array of atoms with just the one non-degenerate level. So the Hamiltonian of the simple case consists of hopping of electron from a site to a neighboring site described by hopping matrix T in this case. So this leads to a very simple band. And, you know, according to Pauli exclusion principle, you know, you can put there are two end places for electrons. So for one electron per site, we got half field band, and this is metal, of course. And the conclusion is not dependent on distance. Of course, this is not physical, and what's missing here is the Coulomb interaction. So if we put the simplest Coulomb interaction, you know, the U term, which is the on-site repulsion into the Hamiltonian, the complete model is the very, very well-known Hubbard model with T and the U parameters. And the model was first proposed by Hubbard in the 60s, and along with a couple of other scientists. This model is very important in condensed matter physics because it is thought to capture the essential physics of high temperature superconductivity, magnetism, and many other emerging quantum phenomena. The model, you know, looks very simple, but this is very deceptive. The exact solution exists only in 1D, and in 2D and the 3D, it's very, very complicated. You know, although we are getting better with all kinds of numerical methods, but still some kind of a physical realization of the model in 2D and 3D can play the role like a quantum simulator. Therefore, you know, it has a very important role to play to solving the strong correlation problem. So, when you consider a 2D Moire system, like what I'm showing here, when you place, overlay two monolayers of van der Waals material with a small twist angle or a lattice mismatch, a Moire pattern emerges. And they form periodic potential. You can think of them as artificial atoms. They can trap electrons and form a lattice. And this is an example of two transition metal dichotomy semiconductor, with slight lattice mismatch, but 0 degree twist angle. And you get a period on the order of 8 nanometer. So the reason, why Moire is a very interesting platform to study correlation physics is because it introduces new length and energy scales. So on this kind of a very dimensional analysis level, if we have the Moire lattice period on the order of A, then the interaction energy, I'm not considering strong Moire potential yet, inversely proportional to the distance. On the other hand, the bandwidth of the lowest electronic miniband is proportional to momentum square, which is inversely proportional to distance square. So the ratio of interaction to the kinetic energy scales like an effective mass and also the distance. And this value can be relatively big for the semiconductors I'm going to talk about, because mass is on the order of half electron mass, and this period, Moire period, is on the order of 10. So this can be immediately on the order of 5. And if you consider the effective strong Moire potential, it can confine electrons much better, and therefore to increase this number even more. So Moire materials, of course, are not stranger to you guys. And we have been inspired by the early work of Yuan Cao and Pavlov. So it all started with twisted bilayer graphene. And, we were still amazed by the new phenomena emerge from the system, superconductivity, correlated insulating states, quantum magnetism, and many more. So when we started this line of work, the question we ask ourselves is, can we make the correlation physics a little bit easier to access? Because correlation occurs in twisted bilayer graphene only near this so-called magic angle around 1 degree. Therefore, if angle is slightly different, the physics from different devices will look somewhat different. So we would like to have a wider range of so-called magic angle, more robust correlation physics, and perhaps, to make the problem a little bit simpler, if we can have a well-isolated single band. And this is the motivation to go with the monolayer semiconductors. So let me just give a few words about this class of material. I'm sure most of you have already heard about this or maybe worked with this. So this is very similar to graphene, but the main difference here is, although it also forms a kind of a honeycomb lattice, but now the A and the B sublattice symmetry is broken. And it's a semiconductor. In the limit of a monolayer, we have direct band gap at the Brillouin zone boundaries, K and the K prime point. So the energy gap is on the order of 1 to 2 eV. It has very strong spin orbit coupling. So the each band is spin polarized. And it doesn't break a time reversal symmetry. So when you go from K to K prime, which is minus K, the spin also flip. So this is so-called spin valley locking. And it leads to some very interesting optical selection rules, which I will talk a little bit later. Okay, so now when you form a Moire, you can think of kind of a Bragg reflection. So this is simple band I showed you, for example, around the K corner, now becomes this Moire mini bands. And the first few Moire mini bands, are quite flat, and this is where correlation physics comes from. Okay, so a couple of years ago, or 3 years ago now, Alan McDonald's group predicted that heterobilayer of TMD materials can be described by a single band Hubbard model with 2 parameters, T, which is the lattice hopping, and U, which is the on-site Coulomb repulsion energy. In place of electron spin, here we can think of its valley pseudospin, because spin and valley are coupled. So still twofold degeneracy. This interside hopping energy has been estimated around 1 to 10 millieV. So this is a very strong function of twisting angle, which determines the period in the Moire superlattice. The on-site Coulomb repulsion energy is relatively big, on the order of 10 to 100 millieV. So those energy scales are between the energy scales in real crystalline solid and also in the cold atom in optical lattices. So after this brief introduction, I would like to tell you a little bit about some results we were able to obtain by studying this system. So I will start with what happens, when you fill the band with half filled band, which is 1 particle per site, because of the double degeneracy. So this work carried out by these 3 gentlemen. We make samples pretty much like, in graphing business. And the only difference now is that we have 2 different materials, and we need to stack them at well-defined twist angle. So we need to determine their crystallographic orientation using nonlinear optics first, and then using dry transfer method to stack them. So we can do it within like a ½ degree accuracy here. And as an example looks like this. We have some electrodes, and here is the heterostructure. The Moire system is encapsulated in hexagonal boron nitride, and we can also put field layer graphite as top and bottom gates. And we can do optical measurements with beam size on the order of 1 to ½ micron, depending on which wavelength you probe. We can measure in-plane transport, and we can also measure capacitance. In other words, compressibility. Okay, so let's take a look at the resistance measurement. So this is from early results. So what I'm showing here is 2-point resistance as a function of filling factor in this combination of Moire. And as you can see here, when we tune the filling factor using electrostatic gating, the resistance changes dramatically. So this is the lowest temperature. For example, we see resistant peaks at filling factor 1 and filling factor 2. So when we warm the system up, you can see the resistance peak goes down, and disappears somewhere here. And the temperature range for filling factor 1 peak to disappear is on the order of 150 Kelvin. So what is the origin of the resistance peak? So the material shows insulating behavior here. So the resistance peak, or the insulating state at the filling factor 2, is very well understood by the single band picture. It's just a band insulator. When the first Moire mini band is fully filled, you see an insulator. So the filling factor 1 insulating state is a little more complicated. It's not a single particle. It's a mod type of insulator. So when the interaction is weak, this should be a metal, but when the interaction is strong, we open up a Coulomb gap. And that temperature dependence, gives an idea of how large this U parameter is. We can estimate that, and it's around 20 millieV. And of course, what's important at the mod insulating state is the magnetic interaction, because after charges are localized, the spin, they become localized magnetic moments. So the magnetic interaction actually determines the low energy, the ground state, and the low energy excited state. So to see this from this simple model, you can treat hopping now as a small perturbation in the limit when U is much bigger than T. So in principle, exchange interaction is possible. But when the spins in the nearing site are parallel to each other, this is forbidden. But when the spins are anti-parallel, you can think of like hop over and hop back. So this is the super exchange pathway. And the energy you can estimate from perturbation theory gives you T squared and over U. So mod insulators in this simple model are antiferromagnetic in the ground state. And the energy scale is determined by super exchange, and it's proportional to T squared over U. So let's go ahead with the magnetic property measurements. So we would like to study the magnetic susceptibility, because for localized moments, magnetic susceptibility is reasonably well described by this very simple Curie-Weiss model. If the material is paramagnetic, the magnetic susceptibility diverges at the 0 temperature. If it's ferromagnetic, then it diverges at Curie temperature, which is positive. And if it's antiferromagnetic, then the susceptibility should diverge. The high temperature susceptibility, you can extend it, and it should diverge at some negative constant. So, it's easier to see when you do the fitting in 1 over susceptibility and just look at intercept. So from experimental point of view, we are probing a device, a sample of about a few microns square. Moire period is on the order of 10 nanometer. So we have something around the 10,000 spins, which are embedded in a large magnetic background. So it's not that straightforward to measure those susceptibilities, and the new techniques, NV center and other ones, are they are coming to tackle this problem. So what we try to do is to use optics to study it, because those transition metal dipole coordinate semiconductors have very strong exciton resonance. So optics is very location specific. So you can probe exact layer of this material. And I mentioned about optical selection rules. So those materials, the K and the K prime value couple exclusively to left-handed or right-handed light. And if there's magnetic moments in the background, those excitons are going to feel the influence of the magnetization from the background. And the left and right circular polarized response will be different. And then the difference corresponds to the magnetization in some limit. So this is just an example, showing the reflectance. You can think of it like absorption of this particular exciton resonance. This is in the case when we don't apply magnetic field. So now once you apply magnetic field, this peak is going to split into two, and you can see them shifted. So you can either look at the shift of the peak or look at a particular wavelength, the difference between left and right absorption. And this is linearly proportional to the background magnetization. And this is the result. You can see that this difference between left and right first increases linearly with applied magnetic field. And then after a little bit over 1 Tesla, the signal saturates. And this is because you can easily polarize the localized magnetic moment. And we can use the slope near zero field to extract the magnetic susceptibility, because this is effectively is an M-edge curve. Okay, so here's the result of magnetic susceptibility, which is that slope as a function of temperature. And more clearly, we can plot as 1 over chi as a function of temperature. So at a high temperature, it follows the linear dependence, and it deviated from it at low temperature, and then a cross intercept is around -1 Kelvin. So what this analysis tells us is that the nature of magnetic interaction is antiferromagnetic, and the exchange, super exchange interaction energy is on the order of 0.1 millieV. Combining with the U parameter we obtained earlier from the transport measurements, we determine T is on the order of 1 millieV, and this value agrees reasonably well with the DFT calculation. And then the ratio of U and T is on the order of 20, and this is fully consistent with the observation of Mott insulating state. And then you can, of course, extend this technique to study the entire phase diagram, which I'm going to skip, so you can look up there. Okay, so now I would like to switch gear, talk about electron crystals, exactly what's happening at the fractional filling of the Moire superlattice. So, in devices when the gates are close to the Moire superlattice, you actually don't need to worry about long-range Coulomb interaction. But if your gates are further away from your sample, for example, if you put it like 20, 30 nanometer away from the Moire with period of about 10 nanometer, long-range Coulomb interaction actually becomes not negligible. They can be bigger than the hopping parameter T. So, so that needs to be taken into account, and it also makes the problem richer. So the complete model should be this extended Hubbard model. In addition to outside the Coulomb interaction, we can also have long range. So what is the effect of long range Coulomb interaction? So for the on-site Coulomb interaction, we've seen that charge try to localize at each site, and they avoid double occupancy. But now if you include the long range, they should also try to expel neighbors. And this is what my colleague Veit Alsa has predicted or simulated using Monte Carlo method. And you can see at the filling half of the Moire site, 2/5, and other filling factors. So let's just take a look at the middle one, for example. So for 1/3 filling of the Moire superlattice, we have one site filled every 3 sites. Or if you switch, black and white dots, you can think of this like 2/3 filled, 1/3 empty. So they try to avoid also nearest the neighbors, and that's what this pattern tells us. And we can also study what is the critical temperature, for those phases to emerge. But experimentally, how do you probe those guys? So we sort of invented this technique we call Rydberg state sensing, and it's like a poor man's solution to this problem, and I think future studies with scanning probe technique, should be able to see those states. So let me just describe to you how we did it. So let's just consider a sheet of semiconductor, monolayer of semiconductor. So it could be tungsten selenide, some other TMD semiconductor. It has very strong excitonic effects because Coulomb interaction in general in 2D materials is much reduced. And you can think of this as a 2-dimensional hydrogen atom, with 1/r potential with some kind of a screening. And the result is, some kind of a Rydberg states, as in real hydrogen atom, we have excitons, with principal number n equals 1, 2, 3, and higher orders. And then they merge into continuum, which is the band-to-band transition, in the spectrum. So the exciton binding energy is very sensitive to the dielectrical background. In a homogeneous medium, it goes like 1 over the dielectric constant square. And also the ball radius changes with the principal numbers. So for instance, in TMD semiconductors, the 1s exciton ball radius has been measured to be around the 1 nanometer, 2s is on the order of 5 to 6, and the 3s would be bigger. So, so we see this as an opportunity for the excitons, to see the surrounding dielectric background. And, pictorially, you can just think of electric field lines, are much outside this material. So if you put a sample, in this case, a 2D electron gas close to it, then it's going to influence the dielectric background. So if naively, when we think that if this 2D electron gas is metallic or compressible, then it will screen the Coulomb interaction between electron hole Moire. Then you get the smaller binding energy, smaller intensity. And if it's insulating, it will screen less. So you see a larger binding energy and a larger intensity for the exciton. So this is how we realize the device. And this is the work of a former postdoc, Yang Shi, who's with Institute of Optics, Institute of Physics in China now. So we built a structure like this. So here is our sample. And now we place the monolayer of TMD semiconductor as sensor on the order of a nanometer away from the sample by using HBN spacer. And then we can apply gates, do our usual thing. And the energy of those materials is aligned such that, when you apply gates, charge for a given gate voltage, charge will go into the sample only and keep the sensor still charge neutral for the entire process. So let's take a look at how it works. So this is our control experiment. We put one layer of other TMD next to our sensor, which is a WSE2. And the spacing here is on the order of 1 to 2 nanometer. And when we apply a gate voltage, this sample becomes charged at this point. So below it's charge neutral and above it becomes n-doped. And you can see from the spectrum that, for charge neutral sample, the sensor shows very robust exciton response. I'm not showing 1s state, which is even much stronger than those guys. And you see 2s, 3s, and sometimes even 4s state. As soon as the sample becomes doped, and you can see that the exciton oscillator strength goes down immediately, and then there's this sudden red shift, and this is the result of binding energy becomes smaller. And of course, the band gap energy also becomes smaller. So that's why you see this red shift here. And 3s, becomes very weak. You almost don't see it. Okay, so I hope with this, I convince you that this could be a sensitive probe of the sort of local dielectric environment. So now let's put this to work and put our Moire superlattice next to our sensor. And this is the result. So what I'm plotting here is the spectrum of 2s Rydberg state from our sensor. The x-axis is the doping density in the Moire superlattice. So positive voltage is electron doping and the negative voltage is hole doping. The color means, if you see blue, that means you have strong absorption, large oscillator strength. Red and orange means small. And this is the energy. So higher energy means also, stronger binding for this 2s exciton. So the impression is that you see many peaks here. So let's just take a look at the most prominent ones at doping 0, at the filling factor of 1 and filling factor 2, we see prominent peaks. So this one corresponds to the band gap of the superlattice. That's the largest gap in the system. This one is the Mach gap we've discussed, and that's the first Moire mini band gap. And you can also see this on the hole doping side, so that looks like a whole Moire band. And then in between, you see a bunch of those fractional filling states. And we were able to match them, extremely well with the predicted ones, from the extended Hubbard model. And once we have this technique working, we can study their behavior, as a function of temperature, and also, so that's thermal melting of this crystalline states, and also, by introducing doping and other parameters. So I would not get into the detail of those. I just would like to point out that if you look at the first two configurations of the electron crystal, you see that the rotational symmetry is broken. And that's something can also be probed using optical technique. So this is the work of Kavli Institute postdoc Chen Haojing, graduate student Zui Tao, and postdoc Ting Xin. So when the system breaks rotation symmetry, it just looks like a bifringent material, right, in optics. So we can put the material in between two cross polarizer, and as long as the major, the axis, this fastness slow axis of the sample is not fully aligned with the polarizers, you see a leakage of a current going through. So using this technique, we can detect the anisotropy very sensitively using optical probe. And then you can also rotate your sample to find out where those fast and slow axes are. So this is a map we obtained for one particular device at the filling equals half. So the color means the amplitude of the anisotropy. And we also describe this using the line segments here. So the direction of line tells you the orientation of the A-axis, and the length of the line tells you how large the anisotropy is. So this way we obtain, this stripe face pattern. And it turns out that a majority of these domains belong to either, the orientation, like the configuration like this, or zigzag, armchair or zigzag. And by the way, I mentioned we can determine the crystal orientation. So we can determine the anisotropy direction relative to crystal orientation. So, and we can look at, the temperature dependence and the doping dependence. So here, some cuts from this phase diagram. So the signal is peaked at half, and when you increase temperature, it goes away. And that's sort of expected from, melting of the half, filling equals half crystalline state. But we also see anisotropy away from those fractional fillings. And we measured the compressibility at the same time. And those regions, correspond to the compressible region. So the peaks, by the way, in this plot shows the system is insulating because capacitance measures how well the Moire screens, the applied electric field. So from this study, we sort of conclude that in addition to crystalline states, like at half, we can also have, somatic pneumatic phases, in such system. Okay, so now I would like to switch to my third topic. I have about 10 minutes left. So all this is kind of curious, but really, in order to learn kind of interesting phenomena, we should be able to tune the ratio between interaction energy and that hopping parameter, and to be able to map out, the phase diagram. So at the zero temperature, we know exactly what's going to happen because, T tends to delocalize the particles and U tends to localize them. So for the system to be metallic, we need to create charge carrying excitations. You will have double occupancy, and the penalty to pay is U, and of course your gain is T. So when T is larger than U, then the system is metallic. So at zero temperature, it's some kind of Fermi liquid. When T is smaller than U, with some critical value of the ratio, the charges localize and it becomes Mott insulator. But the nature of Mott transition, how to go from here and there, is very non-trivial. And this is also a very old problem. People have been studying this for many, many years and decades. And the closest in terms of a material system is those, organic crystals, when you can use the pressure to tune the bandwidth and study the transition, from Fermi liquid to Mott insulator. So our hope is that, this Moire system gives us some kind of a cleaner way to tackle this problem. And of course, there are many of rediscoveries, relearning things that have been forgotten maybe. So how do we tune U over T? So the original technique probed by Alan McDonald's theory paper in 2018, of course, is to try to tune the angle between the two layers, the twist angle. So when you change the twist angle, you change the Moire period, and that can significantly change the hopping matrix element. And U, will also be changed, but much less. But in experiment, it's some groups are trying, and I hope to see some progress, soon. But at this moment, it's still very difficult to continuously tune that twist angle. So we went to different routes. We use, this double gauge structure to play with the electrical field. So the idea is that when you apply vertical electrical field to the Moire potential, you can tune the depth of the Moire potential well. And that will influence the hopping parameter significantly. Of course, it will also influence the confinement width of the charge, therefore the on-site Coulomb U, but that's a smaller effect. And this is the work of those three postdocs and the students. So maybe I skipped the two, let me just quickly go through this. So like a very important motivation for us to do this, is to see whether there is really a continuous Mott-Hubbard transition. And we know magnetic interactions are very important near the critical point, and perhaps this is also a platform to realize quantum spin liquids. And just want to show you this very recent numerical result for triangular lattice Hubbard model single band. And at zero temperature, when you tune the U over T parameter, small U over T, we know it should be Fermi liquid, a large U over T should be mod insulator, and the transition, occurs at this critical interaction strength. And what, those guys found is this very interesting intermediate phase, chiral spin liquid. So that also gives us motivation to search, perhaps there are some exotic magnetic states. Okay, so so what I'm showing here is a 4-point resistance as a function of the temperature, and the different curves correspond to different vertical electrical field. So when we tune the field, and you can see that, the temperature dependence of resistance sort of behave in 2 different behaviors. For this group, you can see that when you lower the temperature, the resistance goes up monotonically. And this is an insulating behavior, right? And this guy is a little bit special. Throughout the temperature range, it follows a power law. And now when you look at the second group, when you lower the temperature, the resistance decreases. And this is a metallic behavior. So just by looking at this, or you can see this a little bit better, this is at the extrapolated 0 temperature, when you tune the electrical field across the Moire, the conductance changes by orders of magnitude within a very small range of this tuning parameter. So we believe we have achieved, insulator to metal transition by tuning the gate, the electrical field. We can analyze the data more carefully. So for example, looking at the insulating behavior at a higher temperature, you can fit them using activation law, and that gives you a charge gap. So the charge gap decreases as far as we can tell to 0 at some critical field. And on the metallic side, the resistance, increases linearly with temperature square, and this is characteristic of Fermi liquid. The coefficient of that T-square dependence is proportional to mass square, the quasi-particle mass square, and we look at this coefficient. It diverges on the coming from approach from the metal side. And interestingly, this mass does not follow very well the power law scaling, and it describes better with this log divergence law. We can now try to collapse those 2 groups of data, the insulating one and also the metallic one. And the scaling works reasonably well, when we look at the ratio of the resistance to that critical resistance, and come up with T0 parameter, rescale the temperature, and this T0 is dependent on the field. And you can see that, those 2 are symmetric. You have a symmetry here. And this plot shows T0. It closes down towards that critical point from both sides. And interestingly, this T0 and the charge gap almost follow the same scaling law. So let me just summarize the scaling law. It's summarized here. So this is the charge gap, and that's the T0 parameter. So we have 2 exponents, and you can think of this like a scaling for length scale or the scaling for the time, right? And those are the values from experiment. And we try to compare our result to some theory. So here is a theory from Sentil back in 2008. So he considered continuous metal insulator transition from Fermi liquid to spin liquid. So it's paramagnetic mod insulator. And because you have the charge and the spin degree of freedom, so here actually he predicts there should be two crossovers, and that's something we are still learning. So any comments will be very welcome. So compare our experiment to this, the prediction of this theory. It looks like we have a reasonably good agreement. And of course, this is still very preliminary. We're still working on this, both in terms of, those exponents, mass, log divergence, and we also measure the magnetic susceptibility. We didn't see any singularity, and he predicts that there shouldn't be any singularity. Okay, so with this, I would like to finish my talk. So I hope I convince you that semiconductor Moire systems provide a very unique platform to study the Hubbard model with highly tunable parameters. I talk about three things. At half filling of the band or full filling of the superlattice, we have observed antiferromagnetic mod insulating state when U over T is large. At fractional fillings, the long-range Coulomb is also important, and we observed electron crystal states using the Rydberg sensing, exciton sensing technique. And I also talk about some recent results on tuning the interaction strength and see, the Hubbard transition. And of course, there are many open questions. Are there exotic magnetic states? Can the system be superconducting? And if yes, is this conventional or unconventional? So far, we've talked about the triangular lattice. Can we tune the lattice symmetry? Because we know this is important for magnetic interactions. So far, I've talked about putting electrons into those traps. Can you put bosons, in this case would be electron holes, into those traps? Can you dynamically change the Hamiltonian, do quantum quenching or related experiments? And can you observe dynamic quantum phase transition? So with those bunch of questions, I would like to stop here, and I'll be happy to answer questions if you have any.
Great. Thank you very much. A very interesting talk. I think for questions, one way to do it is if you can type the question into the chat window in Zoom, and then we can address them that way. I guess to start out, could you tell us a bit about superconductivity? Because when Pablo looked at twisted graphene, then they found both the mod insulator plus a superconductor. And I guess the theory of that is still being figured out. But what do you think about superconductivity in this context?
So first, the experimental evidence, so far, we haven't seen any. Okay. And I have no reason to, to doubt that there shouldn't be superconductivity. I just think we haven't found the parameter space to see that.
Uh-huh.
Yeah.
Yeah. Okay. Let's see.
So there are two Q&A.
Can you see those?
Yeah.
Oh, okay. Go ahead then.
So is the mod insulator a special case of an electron crystal? Yeah, I would say that. So Philip, for the Fermi liquid to Moire transition, what is the critical resistance you measure? So let's go back to the curve. So Philip, can you see this? So it is, you know, on the order of the universal value, but you know, not. So a few times of that, or a fraction of that. So maybe it's better to see the previous one. Is this
Okay.
2-terminal or 4-terminal? This is 4-terminal measurement.
Other questions? You can, let's see, and typing them in Q&A is good. Oh, here we go.
I have a question regarding the Moire-Hubbard transition. What do you expect to see at the critical point if you perform the same optical measurement in WSC2, WS2, where you see the stripe faces? So this is a very interesting question. I didn't mention explicitly, you know, those two experiments have been done in 2 different material systems. And the reason is because you saw the estimate of U/T ratio I put up for WSC to WS2 system. You know, it's on the order of 20. So it's too large to start with to be able to cross over experimentally. So assume you can do this experimentally. So my feeling is that you should still be able to see those stripe faces. And the reason why, you know, I think that's possible is because, you know, the stripe faces have been discussed in high TC materials quite a lot. And I think, you know, here the U/T is getting similar to those systems. Are you happy with my answer? Okay, I don't see any answer.
It sounds good. Thank you. I think they can't speak the way the Zoom works in this mode. Any last question? Please type away. Okay, if not, thank you so much for your talk. It's really quite interesting and really excellent results. And thanks very much for giving it.
Thank you. Bye-bye.
Bye-bye.
Bye.